My name is Daugherty. I'm the Chief Technology Officer for the Motor Equipment Manufacturers Association. I'd like to thank everyone for coming today. I'll introduce our panel as we go through the presentations here, but we're here to talk about the challenges facing battery electric vehicle adoption in the U.S. So next slide. I'll go over a couple slides here just to get things kicked off, then each of the speakers will have a brief presentation, and then we'll have a discussion among the speakers, and feel free to ask questions during that discussion. So on your screen in front of you, you see light vehicle plug-in EV sales. That includes plug-in hybrids as well as full battery electric vehicles. You can see between 2017 and 2018, the purple line in the middle is the total light vehicle plug-in sales. The top line is car sales, and the bottom line is SUVs and light trucks. So you can see that there was a big jump between 2017 and 2018. Then we had kind of a plateau there for a couple years, and people were wondering what's going on. Now we see, obviously, this year sales are starting to go up as you have more and more models available. It's still only about 3.5% of U.S. total sales, so a long way to go to get to the 10, and then ultimately the president's goal of 40 or 50%. So we'll see how that goes. Next slide. So I'd just like to lay out some of the challenges that are out there in terms of this conversion to battery electric vehicles. So one of the biggest challenges, I think, is the discussion starts with zero emission vehicles, or ZEVs. Really, there's no such thing as a ZEV, as every engineer knows, but the general public doesn't understand that. And I think we need to get to a point where we're looking at the total carbon that's generated by vehicle systems, including the fuel and the production of the batteries and other components, to have a real discussion. Because saying there's zero emission vehicles assumes that there's green power available everywhere. There's a consumer acceptance issue. Obviously, this is a big change for consumers in terms of how they act with their vehicle, especially on long journeys. So there's also a high cost penalty. So you have a lifestyle change for consumers, as well as a higher initial cost for BEVs. And we've seen over the last several months, and actually the last year and a half, some pretty expensive recalls from several major manufacturers. So as you push a technology pretty hard, you don't have that benefit of a kind of a long glide path into a new technology, and you can have some difficulties. We've also got many vehicles fighting over unknown demand. In the US, in 4 years, we're going to have about between 125 and 140 BEV models for sale. So that's just in 4 years or so. If sales are around 10%, you're talking about relatively low sales per model. And then also, we make the world's transportation system grid dependent. So if you have a solar flare and it takes out the electric grid, it's not just a problem for homes and factories, it's now a problem with all the rescue vehicles and people transporting goods and personnel around. Next. So the media focuses on very high power DC fast charging stations, public charging stations, as one of the main impediments to battery electric vehicles. But we know from data that between 80 and 95% of consumers, depending on the surveys you read, charge either at home or at work. There's many reasons for that, but you really need, as was mentioned in the last panel, you need to have significant range so that you don't have that as a worry during your normal week. One of the other issues is how many residences can support charging. If you live in a single family home with an attached or detached garage that has 220 power, you're all set. For $1,000 or $2,000, you can be set up to do a relatively fast charge. If you live in a brownstone with on-street parking or an apartment high-rise, you're counting on somebody else setting up that charging capability for you. So that's something that I haven't seen any studies. I've asked a number of the study groups that we work with to look into that, and they're starting to, because I think that would be an interesting analysis to see how many homes really can't support electric charging today. The other is high-speed charging. The infrastructure is quite important. Obviously, you're looking at getting a lot of power to one location. And talking with the electric companies, if you want to get up to 3 megawatts of power somewhere, 6 to 8 months to plan and install, that's a pretty good rule of thumb. But if you want over 3 megawatts, in most of these charging facilities, if you have 10 or more chargers, you're talking about over 3 megawatts of power. You're talking about a year and a half or more to plan and install that. The other issue is we have significant power consumed by these. So when you plug in a vehicle, it's equivalent to to a DC fast charger using 300 kilowatts, which is at the high end as an example. About 250 homes, average power use coming online all at once. So if you have a station with 10 of those chargers all coming on at once, you're turning on a subdivision, so you're talking a significant amount of power, just to kind of give you an idea there. All right, next. So as I mentioned, most charging occurs at home, and one big reason for this that gets overlooked is that if you use a DC fast charger on a trip, that power you're using costs 3 to 4 times as much. Because of the cost of the chargers, because of the cost of the infrastructure that goes into that, and because they're not used that often, they have to amortize that power over the users that are there. So you're paying 3 to 4 times as much per kilowatt hour using that DC fast charger. That's another inducement to charge at home or at work. So on the commercial vehicle side, we have last mile delivery trucks. I think they're going to be the first to convert to fully battery electric in very large quantities because you have very consistent, well understood routes. So you're talking Amazon, UPS, FedEx, those types of trucks, mail delivery. You have daily hub-based operations where they go back, they can charge the whole fleet at night. And these really, people talk about, light vehicles being these primarily, but really you could have medium or heavy duty vehicles in the same mode. It's more important what the route looks like and what they need to do during the day than the size of the truck. Next. And then some of the biggest challenges, we already mentioned station capital costs, but the low typical usage in a DC fast charging station is one of the biggest problems. You see peak usage during holidays and weekend travel, and everyone wants to use that charging station at the same time. You've probably read articles, people driving from Southern California to go skiing, and Northern California, people driving from Southeast Michigan up to ski resorts or up to the lakes in the summer. They all want to charge at the same location at the same time, and that's when the problems start, because you get lines, if it takes 30 to 45 minutes to charge. Another issue that was mentioned in the last panel is battery disposal. One of the things you hear is, we're just going to reuse the batteries, but that's really unrealistic at scale. We haven't really entered into that time because the first Teslas and things are kind of coming towards the end of their life, but recycling is going to be a key here, and the costs of that are quite unknown, so another big challenge. And then one of the biggest challenges is that high-performance hybrid internal combustion engines may actually, in most cases, produce less CO2 over their lifetime than BEVs. Now, I know that's a controversial statement, and it very much depends on how advanced those hybrids are. But it also depends on what's going into the grid. Obviously, if the grid is very green, that's not a true statement. But in most places in the world, the grid is not green. The other issue is if we make a push just towards BEVs and not towards advanced technology across the spectrum, we're really picking a winner, and we're not letting the market work out what the best way to protect the environment is. So with that, I'll close my remarks and introduce our first panelist, who's Eric Varton. He's the Director of Core Engineering for Yazaki North America. So Eric?
Just make sure I know. Forward. Backwards. Okay, very good. Hope you can hear me okay. My name is Eric Varton, Director of Core and Advanced Engineering at Yazaki North America. Appreciate your attention today and being invited to this panel. Yazaki may not be as well known as some other suppliers, so take a couple slides to introduce ourselves. Yazaki is a global Tier 1 supplier of electrical and electronic components and wiring. We were founded in 1929 in Japan. We are privately owned. We are a global company. We operate globally in over 40 countries. And we have been in the United States and involved in the automotive industry for 55 years. A few interesting facts about Yazaki. More than half of all internal combustion engines in 2002 contain Yazaki content. More than half of all hybrid electric vehicles also have Yazaki content. And most interesting and important, more than half of all fully electric, battery electric vehicles contain Yazaki content as of those produced in 2020. And our global net sales are just under $16 billion. With this slide, just a quick introduction to some of our products: electrical distribution, wiring, connectors, terminals, wire, and other provisioning components. power electronics that do power a lot of the hybrid and battery electric vehicles, onboard chargers, DC to DC converters, as well as battery electric centers. We do electronics and instrumentation. That includes needle gauges, flat panel displays, human machine interface, and heads-up displays. And then more importantly, we have almost 3 decades of experience in high voltage wiring, connectors, systems, and architectures. Some of the challenges, and Brian laid out some of those, to adoption of BEVs. And of course, battery vehicles are not something that's new. The idea has been around and courted for over 100 years. But the stigma, the styling, and the performance certainly are ones that recently I think we've overcome. What's interesting about the early stigma of having an electric vehicle is now replaced with actually the prestige of owning an electric vehicle in most cases, especially with the launch of most of the luxury models that we're seeing first introduced into the market. Again, styling, either small cars because of the limited capacity of the batteries, or retrofitted vehicles with cumbersome batteries that intrude upon the operators or the practicality of the vehicles. And now you can get a vehicle in large, small, SUV, off-road. The offerings are really amazing, and the ones that are coming are going to be even better. On the performance front, it used to be that performance was not that good, and now today I think it's easy to say that the luxury performance BEVs can outperform internal combustion engines on acceleration and drivability. So today, the challenges today to adoption of BEVs. Obviously, we talked about a range anxiety. It was mentioned in the last panel discussion. I think the anxiety is real by the consumers, but I think it's unfounded. Most cars today have more than enough range for daily drivers. Charging time, I think we're addressing that. As Brian mentioned, the majority of that is done at homes on AC chargers, which typically take 4 to 12 hours and give you about 30 miles of drive time per hour of charge time, or 30 miles of drive per hour of charge time, versus the level 3 fast charging, which typically will give you about 100 miles for 1 hour of charge. But again, those, because of their power requirements, are really not something you're going to find in a residential setting. And then charging infrastructure. Are the chargers where we need them to be? Are there going to be enough of them? Interestingly, in March of 2021, we passed the 100,000 count for fast chargers in North America. We have additional investment promised by the Biden administration, almost $15 billion, to get that number up to 500,000 by 2030 in support of battery electric vehicles. So they're coming. And then lastly, the ongoing challenges, right? The overall cost of ownership, the sticker price is higher. There's incentives to help get that down, tax incentives. But I think the first adopters and the luxury models that come out will help to fund, I think, a lot of the reduction and building up of the supply chains that we'll see that will allow those to come down. Vehicle safety is huge. We've seen a lot of salacious articles in the auto news about recalls and fires. Electric vehicles are safe. They aren't without incident, but neither are internal combustion engines, and we'll need to continue to address that both in the media and in our designs. We want to make sure that BEVs are safe. The products that we make help to make them safer, safe for the occupants, safe for the drivers, safe for the service technicians, and also safe for our first responders, should they be needed. And then lastly, sustainability. The reason for electrification, for plug-in hybrids, and for battery electric vehicles is we want to make we want to have less of an impact on the environment. And we need to make sure that we look at the full life cycle of the new materials that we're using to lightweight and to power the batteries in the vehicles. And we need to make sure that the entire life cycle and impact on the environment is known, so that we're making the right choices going forward and not actually working against the ultimate goal. And with that, I thank you for your attention and look forward to the panel discussion. Thank you very much.
All right, thank you, Eric. Next up, we have Kevin Calzada. He's the Global Product Strategy Manager for Eaton. So, Kevin.
Thank you, Brian. Thank you for coming to join us today here. I'm going to be talking a little bit about a different topic that actually Eric mentioned it, which was great, but it's one that doesn't always jump to the top of the list when it comes to what are the roadblocks when it comes to electric vehicle adoption anywhere, and that's the topic of electrical safety. And before I get into that, I'm going to just want to give you a little bit more background of Eaton and who we are. Our business is split into two different segments. We have our electrical business and our industrial business. And I'm here representing the e-mobility business, which is part of our industrial sector. And we formed this business about 3 years ago. And we took all sorts of different components and elements of existing business that we had in the high voltage electric vehicle space, and we consolidated it into one business that's exclusively focused on electrification of vehicles. So one theme that you'll notice as you look throughout the Eaton portfolio as a whole is there's a strong focus on safety. Electrical safety being one of the strongest ones. And I actually come from our electrical sector within Eaton. And a lot of the expertise that we have as a business, we can now apply it into the mobility section. And in many ways, you could think of the industrial electrical applications in some ways being much more challenging and much higher voltages, much higher current levels and fault currents. So in some ways, we're actually scaling back and trying to bring our expertise at a different scale into the mobility market. So to start, if we had to really boil down what are the challenges with electrical safety, I would make the argument that consumers are concerned about the unknown. And oftentimes, statistics themselves don't actually play a significant role in how concerned somebody is about adopting or purchasing an electric vehicle. We see a lot of articles out there and headlines about vehicle fires, faulty circuit protection devices, and then also the challenge with first responders. I keep hearing about these untrained first responders not knowing how to respond to a potential electric vehicle crash. The issues are just very different. And because of how different and unique all of these different scenarios are, consumers are concerned. Whether or not it's founded, they are concerned, and that's something we, as an industry, need to be able to respond to. And I'm going to dig a little bit deeper into a more specific topic of electrical safety here, and just starting with a very simple concept that as either you're maintaining or whether it's servicing or responding or even just occupying a vehicle, you have to be able to turn it off, right? Very simple concept. You could think of this very simply as a parallel to what you have in your home. If you have a fault condition or if you have a need to maintain or upgrade a branch circuit, then you need to be able to shut off your circuit. And that's what your load center or your breaker panel in your home can do. The same requirements exist for electric vehicles. So I'm going to take this concept of turning off at one level deeper and apply this to EVs. And what does this really mean from an electric vehicle standpoint? How do you actually de-energize and turn off a vehicle? It's not as simple as it might sound. So the first step that needs to happen is you need to be able to electrically isolate your battery. And that's typically achieved through the high voltage switches or the high voltage contactors that are typically found inside of the battery pack. That's step one. The second step is that you need to de-energize what's referred to typically as the DC link or the whole DC system within the vehicle. And that once that's de-energized, that's primarily focused on de-energizing the inverter capacitors or the DC-DC converter capacitors within the vehicle. And then the final step is to prevent any type of additional power regeneration, like from your rotors. So these consecutive steps need to be able to take place in order for you to fully de-energize a vehicle. And one of the biggest challenges that we have is that when it comes to, it all starts with the contactors. It all starts with being able to isolate that stored energy inside of the battery pack. If you can't achieve that, it becomes impossible to address the next two items. Now, why is that an issue? Why is that a challenge? It's because one of the most common fault cases that we see from many discussions we've had with a wide range of OEMs on this topic is that one of the most common fault modes is that these contactors can commonly weld shut. So what does that mean from a de-energizing standpoint? If your contactors are permanently closed and welded shut, you can't isolate your battery. You can't make it safe for to work on, whether it's for maintenance, for first responders, for all of these risks that are introduced that come down to this very simple component that sits inside of the battery pack. So I'm going to talk a little bit about a solution that we have come up with to be able to help address this issue, but I also want to comment on this a bit more holistically, that this is a technology that I think is a good example for how the industry, and Eaton in particular, has responded to the need to address this electric safety risk, right? There's many other nuances and many other challenges in the theme of electrical safety that we as an industry need to come together on to address. But speaking about this one in particular, this is the Breaktor. It's a circuit protection and switching technology that we launched a few years back. And fundamentally, the way this works is that it works to prevent the contacts from welding. So even after you have some type of fault condition within the vehicle, this device can still be switched off, and you can isolate your battery, and it doesn't suffer from the welding phenomenon that's very common with some of the traditional components. The second point to make here is that it's also an active or passive device. It works in both ways. And what I mean by that is it can be what we call a self-triggering device that can sense and trigger itself in the presence of an unsafe fault, or it can be an active device that responds according to an external event, like from the airbag ECU, or even just from the BMS. And then finally, I think the final concept here is just around the functional safety being designed into this product from the ground up. We see more and more cases where functional safety is at the forefront of vehicle designers, especially electric vehicle designers. And we've incorporated a lot of features into this product to help our customers achieve their functional safety goals. So in closing here, I just want to touch on a couple points. One is, I believe Breaktor is a solution to help address this one area of electrical safety that we've seen OEMs have a lot of challenges with, right? The industry as a whole needs to respond to many of these other challenges in order to continue driving more and more adoption. But the bottom line is that safer electric vehicle systems will mean fewer events, fewer headlines that we all have seen in the newspapers. And fewer events means that consumers are going to be more comfortable buying these products. And I think that's something that we all need to really strive towards in order to boost consumer confidence in this area. So, Brian?
Next, we have Greg Deveson, President of Automotive at Lyten.
Thank you, Brian. It's actually Lyten, and we did have a little bit of a shout out earlier from Sandy Monroe. I'd like to thank him for that, for the advertisement. First off, good afternoon, and it's really a pleasure for me to be here to represent Lyten today. I'm coming to you with 37 years in the auto industry, the vast majority of which was with General Motors, followed by time with Magna, and then American Axle. A couple of months ago, I joined a Silicon Valley-based company, and I'd like to start by telling you a little bit about us before I get into the subject of the day. Lyten was founded in 2015, and we are the inventor of three-dimensional graphene. The company likes to think of ourselves as an advanced materials company, and we're currently in supply of product, our battery cells, to the Department of Defense. Later this year, we'll be launching a 3D graphene fab and a pilot cell fab for manufacturing batteries. This will be the first of its type in the Valley. Following that, we intend to break ground early in 2022 on a first gigawatt factory for battery cell production, as well as graphene fabrication to support that fab. Now, it's important to note that probably nobody in the audience here today has heard of us, and that's in large part because we've been running in stealth mode for the last 6 years. And in fact, tomorrow, I'm pleased to say that we'll have our coming out party here in Detroit at Motorbella. So what is three-dimensional graphene? Well, I'd like to say this is really the fundamental difference of our product versus others on the market today. By using proprietary material synthesis, which is a green technology, we are able to produce graphene with very unique, highly engineered morphology and electrical features. As depicted on this scanning electron microscope image on the screen, you can see three-dimensional graphene that we use for our cathode to cage sulfur deep inside of these wide array of nanopores. This is the fundamental difference of our product versus others that have come before us. The DOE, or Department of Energy Technology Roadmap for battery cells, is shown here on the screen. You can see that according to the DOE, lithium sulfur advanced battery solutions were not intended to be discovered or commercialized until 2028. You can see that those cells are projected to provide 3x the gravimetric energy density of today's lithium-ion cells that are available on the market, and 2 times the expected energy density of solid state. So again, looking at the technology, these 3 lithium-ion cells can be replaced with 1 lithium sulfur cell from Lyten. And we're pleased to announce that today we intend for these lithium sulfur cells to be available in BEV applications as early as 2025, 3 years ahead of the DOE roadmap. Well, now that you know a little bit about us, I'd like to shift gears and talk a little bit about the challenges we see driving BEV adoption in the United States. Research from Bloomberg would highlight 4 key areas that are limiting BEV adoption today. First, as already spoken about by previous panel members, consumers must be confident in the technology, and they have to be willing to make a choice for a BEV over conventional ICE or PHEV technology. The good news is that statistics would say 70% of today's consumers are giving consideration to BEV technology out of concern for global warming. Now the industry needs to make sure that consumers don't have to give up the design aesthetics, safety, performance, convenience, and features that they've come to love from their ICE brand of choice. In fact, we need to make sure as an industry that the experience actually offers a better product at a better price. And importantly, as part of that, the technology must be affordable for everyone, and the OEMs and the supply base must be able to generate acceptable returns on invested capital. Based on recent announcements, all of the established global OEMs have made multi-billion-dollar investments in all new electrified architectures. There is little doubt that they are committed to an all EV future and have aligned their product strategies accordingly. Beyond Tesla, there are also several other startups that we're reading about today that I believe are bringing distinctive products, capable products to the market, and I believe this will be very good for our industry as it will promote further competition, leading to further improvements in technology, quality, delivery, and cost. Finally, in the US, we're starting to see some nominal improving signs of state and federal government adopting policies and legislation that will help accelerate BEV adoption. This will be imperative to support the massive investments that are needed in technology, infrastructure, the supply chain, and people development. By most measures, China and the European Union are far advanced of the United States in making and adopting EV policy today. I'm hopeful that this will change, and it will be critical, in my view, to our long-term success as a nation. It should come as no surprise that I am a firm believer that innovative technology, coupled with the incredible capability of Detroit and its supply base, like many represented here today, will lead the way to solutions with maximum range, optimized packaging, better safety, faster charge times, and of course, improved sustainability and recyclability. All of this enveloped with an improved total cost of ownership experience. I can envision a day 10 years from now where we will be attending conferences like this and they will be dominated by battery electric vehicles. I believe our planet and our grandkids will thank us for it. So please come and see us just through that wall in the tent there. We are Lyten, we are at booth 300, and we would love to answer more of your questions about us following this panel discussion today. Back to you, Brian.
Thank you, Greg. And our final panelist is Jack McCauley from the Jacobs Institute for Design Innovation at UC Berkeley. Jack?
Hello, thank you. I teach vehicle engineering at UC Berkeley. I focused on motor physics, controllers for EV motors, and I also have a private R&D facility which we build electric vehicles. Today's talk, I'm going to give you some sort of calculations that we've done there about sustainability, carbon emissions and so forth at Berkeley, and these are real numbers, and I just wanted to delve into this a little bit. My slide deck isn't particularly long. I'm going to comment on something one of my fellow panelists said here, which is in regards to the charging capacity. It does impact the grid. Taking your vehicle to your house and charging it up. A level 2 charger is about 8 kilowatts, and it takes a 60 kilowatt hour car, which would be like a Chevy Bolt or another Tesla Model S, an older Model S, takes about 8 hours to charge at 8 kilowatt hours, and that's stresses the electrical system. If everyone comes home at 5 o'clock and plugs their EV in, the system's not designed for that. So we're going to have to upgrade if we're going to continue forward with EVs, we're going to have to upgrade the utilities. In California, it's problematic. The largest utility in the state is PG&E. PG&E is encumbered with legal problems and financial issues. From what I've seen, I don't think that PG&E is going to be able to do this. Some of the areas have their own private utilities. San Diego has their own utility, Sacramento, and Santa Clara has its own utility, but PG&E is the largest supplier. How they're going to do that in the future is an unknown, and this is maybe a policy issue also. So let me go through the deck. I mentioned I teach motor physics. We're also working on new motor designs for EVs, more efficient motor designs. The current motors, like the Model S motor, is an induction motor. It's a very simple design. It's running about 92% efficient. There are newer motors coming out that increase the efficiency by about 4%, and there are also induction motors of a not so similar design. That's kind of what I'm working on in my facility. We're going to build a new motor, and with variable magnetics in it. So here's the sort of the takeaways here. Are EVs efficient? Depends. It depends on the electronics on board, the batteries, the motor design, and that is true. They are efficient. A gasoline-powered car runs about 37% efficient for a really good car. The most efficient internal combustion engines run about 40%. The powertrain on an EV is about 95% efficient. So for every calorie you put in, you get 95% of that out. For every calorie, if you will, that you put into a gas-powered car, you get about 37% out. The rest is heat that exits a vehicle. So they are true. It's true they're efficient. They're not particularly environmentally friendly. Where the batteries are mined, they're currently lithium. There's other chemistries that are coming out and available, solid-state batteries, and former speaker mentioned his sulfur lithium battery. The mine is a mess. It's a slurry of lithium that is pumped out of the ground, and it's not environmentally friendly, and it has to be mined and purified. That process is environmentally costly, and lithium is also a pretty scarce resource. It's not like you can walk outside and grab a chunk of lithium on the ground, lithium oxide or whatever you have on the ground. It doesn't really exist that way. You have to get it in places where it's maybe not the friendliest place to get it. And Afghanistan is mentioned as a source of lithium, not now, but future source. That's just the kind of place where you don't want a mine can the United States enforce environmental regulations on foreign countries? They haven't been too successful at that. So the things are going to get stripped out of the ground and mined, and it makes a mess. Their trip time, it depends. I have a Model Y. I can get to LA on that one charge if I want to scare myself. There's one charging station, fast charging station, about 2/3 of the way trip from San Francisco, where I am from, that you can charge up. And if you're lucky, it's full of Teslas getting charged on the way down there. So I just prefer to fly rather than drive down there. I can just get on an airplane. So that's not environmentally friendly. For local traffic, 100 miles commute, they're great. They work great. A lot of places in Silicon Valley have charging stations. Apple has charging stations available for employees. A lot of companies make those things available, so it's pretty easy to get a charge on it. My facility has a charging station in back, a level 2 charger, which is 8 kilowatt-hour charger in back that you can charge your car. So they're available. They cannot prevent climate change. There's some numbers that we did on this, and we're looking at, like, if you have a gasoline-powered car, how many trees do you need to plant to go 10,000 miles a year? And it turns out you need to plant about 300 trees, full-blown trees, like big trees. They're not particularly environmentally friendly, and why is that? Well, if you look at transportation, there's a pie chart. If you look at transportation, it only consumes about 30%, 37%, 30% of the global CO2 emissions. What do you think is the biggest consumer of CO2 emissions? And it's kind of surprising. It's on industrialization. Making concrete is a bad CO2 emitter. You have to burn natural gas or coal or whatever you're going to burn. So if you wanted to really impact climate change, probably working on the industrial part of this equation if that's a priority for you. Are they less polluting? I just have my 2-second speech about pollution, and I'm from California. I remember LA in the 70s, 60s and 70s. When you looked across the LA basin, you couldn't see the other side. Could not. It looked like smoke. And they call it smog, right? And that doesn't happen very often anymore. Matter of fact, if I'm out in Malibu and I look across, I can see the other side of the valley, and that occurs regularly. Once in a while it gets smoky there, but so regulation has impacted the environment pretty substantially, and I think some of it's good, some of it's not so good, but for the most part that paid off. The catalytic converter, which is placed in your car for emissions, is really been a remarkable device, and every new car has a catalytic converter in it for converting hydrocarbons into non-harmful components. They are mechanically simple. If you look at the Tesla, we have done teardowns on portions of their technology. Tesla, their plant is about 20 minutes from my house, and I go over there once in a while, and we tore down their stuff. It's very, very simple. There's a gearbox and a motor attached to it, a differential and a motor attached to it. That's all there is to it. But the software part of it, it's a software-driven vehicle. It's largely software. The controller algorithms, the monitoring of the batteries, safe operating area, that's all done with computers on board. It's a computer-intensive car. As a matter of fact, when I ordered my Model Y, I was told it's going to take you, 12 weeks or 14 weeks to get it because we don't have chips right now. And I got it sooner than that, but I also personally don't like the Model Y. I have a Chevy Bolt. It's a much cleaner implementation and more user-friendly. I struggle to get in and out of my Model Y. That they're more convenient. I feel that it's convenient, and I think the data backs that up. So we crunched the numbers on this, and it turns out they are convenient. That they last longer than gasoline cars. Potentially, there's induction motors like the Model S that are sitting in chimneys in factories that have been there for 50 years. They've never broken, they've never been serviced. And they, essentially, with the Model S is an induction motor, and they last forever. The bearings and other components like that go out. You need to be serviced, of course, but they last forever. I was talking to Henrik Fisker about his enterprise there, and he was saying, well, it's potentially true that there could be a market for the chassis and powertrain on an EV and just replacing the body, like you get a refreshed body on it because the powertrain is going to last 1 million miles. I think that's kind of a cool observation, that you could get something that lasts that long and it's environmentally friendly. I talked about the efficiency. 96% is for the newer types of electric motors. They're very, very efficient, very low loss. Induction motors, there's 2 types of motors on a Model 3. One is more efficient than the other. They're running at about 96%. And 40% max for an internal combustion engine is pretty substantial. The ones that are the most efficient are on these little generators you buy on Amazon, for camping. Those things are very efficient. They run at maximum power. They're designed to run that way, and they're very efficient. So here's the other part, and this is kind of obvious, I think, that the power that you power your car with, you think it's coming from renewables. It's not. It's coming from coal, which is burned somewhere else in the United States. And in our case, PG&E buys the power from these places, and it goes to charge your car up. You do get a hit there in efficiency. So to summarize this, the net efficiency of an EV is about 55% if you compute how the material that's used to make the electric power. Sustainable windmills, you can't put windmills everywhere. You could do it here probably today, but you can't. And solar panels, you can't put solar panels in San Francisco. They don't work. It's overcast all the time. I live in a suburb. I have 108 solar panels on a piece of building that I have there. That's enough to run the house, and it's a farm, and run a farm that I have next to it. Those work pretty well. I've also have batteries. I battery backed up my house, so if the power goes out, I got juice. And the batteries are charged during the day, and I run on batteries at night, so I'm off the grid, essentially. I could charge my car from that, and this efficiency number doesn't apply because I'm not using PG&E or you're the gas company, but basically you're burning natural gas or coal to make the power. So the net efficiency, they kind of lie about that. So if you look at the net efficiency of an internal combustion engine car, it's about 36%, including all the losses, and we're running about 55% for an EV. So it's more efficient, but it's not what we hear in the data that we get from Tesla, for instance. I talked about lithium mines here. Yes?
We're gonna have to cut this off.
Oh, sorry.
We're way over the 7 minutes.
Okay.
So.
Thank you.
So just to have some time for some questions here, maybe Eric, we can start with you. What are the greatest challenges to BEV adoption? Are they technical, regulatory, or market driven?
I think it's a little bit of all of them. I think the technology, believe it or not, is further on its way than maybe the regulatory. And I think the other problem with the regulatory and government input is that it's rarely constant, right? We had an administration that just left,
their philosophy on CAFE and energy was very different from the current administration that we have. And so in the United States, we have the potential that, that policy can change. It could change every 2 years, or it could change every 4 years, or it might not change for 8 years. And I think it has a huge impact. The regulation impacts the economy. It impacts how much money goes to funding for certain things. It can shift from batteries to agriculture. So I think regulatory is huge. I think people are very adopting when it makes sense, but it has to make sense for their pocketbook as well as their mind and their plans for their children.
Combination of everything then. Greg, over to you. What do you believe is the main difference in the adoption rate of BEVs in the U.S. And why it's lagging behind Europe and China? And what's your prediction for BEV adoption, by the end of this decade in the U.S.?
Yeah, good. So the main difference, in my view, between the adoption rate in China and Europe is an aligned view around government policy and common aligned direction and its impact on infrastructure, R&D investment, supply base development. And if I think about the space that we're in just for a minute, and was an education for me when you think about where the power plants for these battery electric vehicles come from today. 90+% of power supply, battery supply, is coming from offshore. And that should be alarming for all of us as we talk about a BEV future. And why I decided to join Lyten was really to be a part of changing that. And so I really believe that adoption has to be driven by a good combination, as was commented earlier, on technology, government policy, supply base support and alignment, and then of course education and training in our school system. Where do I believe the adoption rate will be? I believe by the end of the decade in the US, 25 to 30% adoption rate, and in large part based on the bet that the automakers are making today, but we collectively as an industry are going to have to work very, very hard to bring that to reality.
So 25% by the 2030-ish?
Correct.
Okay. Great. So Kevin, you talked a lot about, contactors, basically pulling the power in an event you need to on a battery electric vehicle. Maybe you can talk a little bit more about, are BEVs inherently more or less safe than internal combustion engine vehicles? Maybe just describe some of the differences there.
Yeah, so I would argue that there's very significant differences between the two. And let me actually touch on a comment that Jack made during his presentation. It was about the amount of energy and efficiency when comparing ICE architectures to an electric vehicle architecture. So if you have 35% efficiency compared to 95% efficiency, to go the same distance, you effectively need 3 to 4 times the amount of energy stored in an ICE vehicle compared to an electric vehicle. So when you talk about fault conditions and think about what could go wrong, you could make a pretty strong argument that an event could be much more catastrophic with an ICE vehicle than with an EV, just because of the amount of energy that you have available. Of course, it's chemical energy, not necessarily electrical energy, but it's still energy. And actually, a lot of the data that you see backs it up. Of course, they don't make the headlines necessarily. You don't see the front page of the newspaper around the internal combustion engine that everyone's probably seen one on fire on the side of the road. But the reality is those don't make headlines. But the fact is, it's because it's that consumer sentiment and that consumer kind of concern isn't necessarily based on facts. It's based on emotion. Buying an EV is a very emotional decision for anybody, and if you're not comfortable based on what you're seeing and what you're reading, then you probably won't do it. And that's why we all need to really look at how do we address that emotional buying decision from a consumer.
Oh, great. Good point. Jack, we've got a minute left here, so maybe you had mentioned, I thought it was interesting in your chart that you said, are BEVs better for the climate? And your answer was maybe. What do you think is the best combination as we go forward, looking at trying to really impact the climate change rather than maybe picking a technology? Where you mentioned industrial policy, but what else is on your mind?
Well, can you hear me? Sorry. I don't want to mention this, but we're probably going to have to look for an alternative power source, and we have nuclear technology. Nuclear, as problematic it is for disposing of the waste, is a clean technology. It's safe, and that's probably the direction the country is going to be headed in. The open question, I'll just mention this briefly, what do you do when we stop using the byproducts from manufacturing fuel? Everything we have, our plastic components, everything, are made from oil. What happens to the price of those things? It's got to go up, right? You make less fuel, that stuff's going to be more expensive. So it's unknown, the economic impact, but nuclear is probably the answer for, long term, and it's probably going to come back. Works in France and other places very well, so thanks.
Yeah, no, great answer. I'm a big fan of nuclear as well. A lot of interesting, new, very safe, inherently safe designs out there. Well, folks, that does it for our time. Please help me thank Eric, Kevin, Greg, and Jack for a great presentation, a great discussion.